I feel very fortunate. Kris Van Hees from Oracle has done some really remarkable work with dtrace over the years. I think you first did the port of dtrace to Oracle Linux uh, quite a while ago now, and talked
Oh
about
yeah.
that at one of the dtrace.confs.
Mhm.
Quite well. That's
Yeah.
right. And more recently, and I noticed a video that a presentation you'd given on this. You did some work with eBPF as the underpinnings of a new port dtrace to Linux. So I'm very excited
Yeah.
to hear about it. Thanks for
Okay.
joining us, Chris.
Sure. Happy to. So yeah, I didn't know it was that long ago. Yeah. So but and I mentioned this most of the time, but I think it kind of shows you where I'm coming from. So originally, when we were approached to do a port of dtrace to Linux, that came to me for evaluation, and my general response was, I don't think that's gonna be possible. So they told me to do it anyway. We got it done. It was somewhat painful, but we have come very far since then. And so when we were later asked to see if we could do this on top of BPPF to not have such invasive changes in the kernel to make it possible, again, I pretty much said, I don't think that's going to work. And well, we have it now. So I got proven wrong twice. That should tell you something. So I'm going to talk very briefly what we had before we started working with BPF, and then get into, what happens now that we're building this based on BPPF and other tracing features in the kernel. How does it work? Sounds like a very big topic. I'm not getting into all the details. I just want to show a little bit, what directions we've taken to make this work, get into some of the benefits of doing this. There's a couple of samples I'll give in to show how creative we've had to be with some of these things, and then highlight complications. And then there's more information like the links. So before we started working with BPPF, we pretty much did dtrace the way it was done before in Solaris, which what you had the kernel space producer yet and user space the consumer. So the split was about 50-50, if you would look at lines of code, and it essentially worked the same way. Was same type of implementation. The only downfall of it was that we needed these kernel changes, and there was no way they were going to be able to be upstreamed in the Linux kernel. So we had a pretty big set of invasive patches that had to be applied to the kernel. And that was kind of obviously a big problem for adoption by anybody who wanted to do this. It's not that easy to convince people to add all these patches on top of, a distribution kernel or just upstream kernel. And so it kind of made things more difficult. Plus, kernel changes meant that we had to keep updating these patches. Not ideal for stability, not ideal for overall maintenance. And again, adoption was definitely not something that would benefit from that. So with using BPPF and other tracing features, it's all one component now. Everything lives in user space as far as the dtrace code is concerned. So shouldn't say all, a whole lot. But what we do within user space is these scripts get compiled into BPPF code, and then these programs are loaded into kernel, and everything runs there within the BPPF execution engine. So that means that the actual implementation of how the providers, not how they work, but how you get essentially a dtrace provider presented to dtrace the way that dtrace would want it, based on trace points that exist in the kernel, is all things that have to be done at the user space level. So we have a lot of code there that creates that, but it also means that knowledge about which probes exist on the system now have to be maintained at user space. Before you just ask the kernel for information about the probes you're interested in. In this case, we actually have to have all that information in user space. So that's quite a bit of extra work there. Then there is also a bunch of support functions we need to essentially know how to implement dtrace actions. This again, nothing exists on the kernel. So this all is implemented in BPPF code. And then there's support code for that. There's pre-compiled BPPF code. Obviously, we compile D directly into BPF instructions. And now we have a linker that meshes it all together and creates something that actually works. Interestingly, and this line count obviously is very rough, but it's kind of the same amount of code as existed before. It's just now been shifted into user space and horribly mangled and rewritten into ways that's, it actually does what it needs to do. So I try to make a graphical explanation of how this works. I don't know if this actually necessarily makes sense, but so on the very top where you have user space, that is where dtrace sits. And that's the only real thing that still exists in terms of dtrace code. So it handles the providers, the probes, we have the compiler sitting in there, the consumer, everything. And it gets its data either from perf event buffers, which is where the trace data is stored. And then there's a whole collection of BPF maps that store additional data. Things like aggregations are kept in there. And some of those are used by the consumer, like aggregations to get data. And other of those are only used by the BPF programs, which is kind of then the next layer, which is all the work. So that is literally the D scripts compiled into a BPF program, all the code added into it to make the actions do what they're supposed to be doing. And that is just presented to the BPF execution engine, which then interfaces with all the other tracing features in the kernel, which is kind of the lower level. And the naming here is a little messy. In some sense, it's mostly a combination of K probes for function boundary tracing, or F entry and F exit. Either can work depending on your kernel. The rest is either trace points, perf probes, or U probes. But I kind of split them out so that there's at least maybe a sense of which dtrace probes would relate to what. And I didn't add a slide for this. Probably should have thought of that. It's kind of a little late now. But sometimes a dtrace probe may have to be tied to multiple operating system trace points or probes in order to accomplish the same, functionality. So it's not always straightforward one-to-one. So how it works? Initially, the idea was it's just going to be a straight compile decode into BPF code, replace actions with function calls to pre-written BPF code, and all should work. That's not the case because we had to start thinking differently, where dtrace traditionally has been working completely action-based. And so the way the clauses in a script are compiled, the code has been generated on a per action basis. That doesn't work anymore. So we had to start thinking more on a class base, and then still in the back of our mind realize that we're still dealing with dtrace. So you can't completely shift focus. But it made it possible to take an entire class and compile it into what essentially is be a BPF function. In order to do that, we had to come up with a generic probe context, which dtrace already had. BPF does not. So by doing this, it was possible that you can have a single class which is connected to a variety of different probes that actually may use different mechanisms in the kernel in order to be triggered, but the class can still be compiled one time and just linked into the correct program. In order to make that possible, we had to come up with a way to essentially structure trampoline code, which is the beginning of the BPF program that gets attached to a kernel level probe. And it essentially massages all the information about the probe into this generic probe context, which then also contains the machine states that dtrace needs. And so as far as our BPF implementing dtrace probe scripts is concerned, all probes look the same. They all have the same way of how arguments are presented. They have the same ways of the probe IDs. So they act and feel and look like a dtrace probe, which made the rest of the implementation a lot easier because we could just reuse a lot of the way that dtrace was working. So a BPF program really simply becomes a trampoline that creates this generic probe context. And then we essentially just call the classes that are relevant to that particular probe one by one, with obviously checking in between that if, probing stops, we need to stop calling them and, handling of error cases. But it becomes pretty much just a program. That did require us to have a custom linker. And this is kind of actually, it was meant to be a linker that takes this BPF program with the trampoline and the function calls, and then resolve these calls, pulling in the code for these different classes, some precompiled code, and create a nice package and load that. It turned out to be a multi-stage linker because there is also certain information we need that at the time when we link the program, for instance, we don't know how large certain BPF maps are going to be. So we have to do a second stage where we resolve those contents that are kept in the code using relocations to right before it gets loaded to the kernel to fill in these constants so that the program actually knows, for instance, how big the string table is, things like that. So the benefits for this obviously are that there is no more dtrace specific code in the kernel. And I don't mean these benefits from the dtrace side, it means benefit from the Linux kernel side. Because we usually depend on some patches, even up until, I would say, maybe 2 years ago. We still needed some patches in the kernel to have a feature called waitfd, just made it possible to wait for both the lifecycle events for processes and what is happening with our tracing, CTF to get our type information, and then this KL mod sims, which associates module names with symbols, even if the module has been compiled into the kernel. Because with the Linux kernel, the fact that a module can be either loadable or built in was posing a problem with having a stability of scripts. We wanted to be able to refer to symbols with the module backtick symbol name and not have to worry whether the particular kernel we're running on has this module built in or has it as a loadable module. So that was also something we had to add to the kernel. We no longer need to waitfd. The KL mod sims has now been replaced by the modules built-in ranges file, which is a patch that was upstreamed into the Linux kernel. So every Linux kernel starting with 6.12 will have that if the correct build option is enabled, which it seems like most people do want to use that because it's local. Well, it's essentially zero costs for a running system, and it can really benefit tracing, dtrace, and even other tracers. And we also can now use the type information that BPF provides through BTF instead of the CTF. It's not one for one. For instance, right now, BTF does not provide type information for kernel global variables, which is a real pain. But you can always cast the symbol to the correct type if you need to use that in a script. And in the meantime, we are actively trying to work with the BPF teams to get BTF to actually include this type information as well, which would be a big step forwards. So all this work having been done has resulted in a dtrace version that can right now work with upstream kernels starting from 5.2, which is like pretty old at this point. But it's kind of nice to know that that's doable because we've had to be able to provide support for production kernels that pretty much go back that far. And as I said, there are some limitations, types for the global variables, if there's no CTF, but it's all things you can work around. It's not a deal breaker. Now, the real benefit was that by doing this, we have been able to remain true to the overall dtrace design and operational expectations. So semantically, things should work the way you would expect if you're used to using dtrace. That has required very crazy code in some places. And I wouldn't say it's 100% perfect. But most of the time, when people have come to me that something doesn't work, it's that they don't understand how dtrace works instead of it being a bug. So at least that's happening more and more. So that's a good thing. So since this morning we've been talking about is enabled probes quite a bit. I think I'll use it as a highlight of something we had to do. Given the fact that we no longer have code in the kernel ourselves, means that we couldn't implement USDT probes and is enabled probes the way we did before, because they're using a new probe, which is what we did before as well. But the is enabled probe would, when it fires, then, you know, patch the instruction to make sure that this test would now be evaluated as true. And we would have basically the benefits you had in dtrace beforehand, that it's extremely low cost. We no longer can do that because we can't patch in that way, or at least it would be extremely painful to do so. So we came up with an alternative which may not work with all C compilers, definitely works with, with GCC, and we're evaluating others as needed. But it's using this construct where we can essentially declare a variable that is in just that local scope, which is initialize 0, then do our fake function call, and then essentially the value of that scopes variable is going to be given as the value of the macro. So in code, this still works almost the same way. And for BPF code, in this case, we are given, and I have a typo there, should be arg0, because we are passing the address of this locally scoped, very, short lifetime variable in this probe firing. The moment the probe fires, we can write in a 1, and that is what will then be given as the evaluation of this expression, and code will work the way it should. So it's not exactly the same way as it was before, but it's about the lowest cost version we've been able to come up with. And that was, I think, probably the 5th or the 6th variant of trying to come up with something that was as lightweight as we could do. So if anybody has ideas to improve this even further, we're open to it. Aggregations, really good feature in dtrace. Was a pest to implement, because the way it was working before in dtrace, where the kernel is accumulating, it's aggregating this data, and then when user space is ready to use it, or on a timely fashion, would read it, which generally would result in a buffer swap, and then it would be further aggregated in the consumer, in user space. That doesn't work, or at least we couldn't get it to work, because access to a BPF map, which is where we had to store aggregations, there's no proper way to synchronize. You can't do locking in between user space and the kernel. And we tried to do a mechanism which is similar to buffer swapping, where we kind of swapping 2 elements in a BPF map, and it was horrendous. We never got it fully to work, and we abandoned that whole idea. So we came up with a different mechanism, which we should have thought of in the very beginning, is if you're aggregating in the kernel and then taking snapshots of that and aggregating those in user space, you can either continue aggregating in the kernel continuously, and instead of having these partial aggregations, and then just have user space read from the kernel whenever it needs the data. That has some impact on how short-lived the aggregation data in the kernel can be. So the footprint in the kernel for memory usage is going to be higher. But we felt it was more important to actually have accurate data than to minimize the footprint. So it works. It was even still difficult to get done. And Clear and Trunk are fascinating implementations. Anybody wants to look at our source code and see how we did that, I would definitely suggest that might give you some very good nighttime reading. So complications. The BPF verifier, it's something you get to either love or hate, or both, more commonly both. So it's what makes it safe to have BPF programs loaded into the kernel and executing, because it does its best to make sure that the program cannot do anything malicious to the system. So it tends to err on the side of caution. which means that it may reject a program that is perfectly safe, but it rejects it because it can't prove, well, in a sense, can't prove that it's safe. So it can be very difficult to keep it happy and still write more complex code. Supporting all the kernels is a challenge, in part because of this verifier, because the verifier obviously changed over the different kernel development stages. And so things that it would reject in the past will now pass. Well, it would reject in the past, they pass now. But there are things that it would accept in the past that now it rejects because they changed some of the logic behind it and they felt that would not be safe anymore. So that has been an interesting challenge. And then the overall concept of BPF and the kernel tracing features in the sense of how dtrace works and how dtrace can be used as not necessarily just a one-shot tracing, but you could actually have a tracing session that can be running for a longer time, that is really monitoring the system for quite some time. It's not really the use case that BPF and most of the tracing features have been used for. And so we really put those to the test and came up with some issues that had to be resolved. So one of the problems also is that sometimes with dtrace, at least in our use cases, and maybe we're kind of extreme, but it's not uncommon for us to be probing 1,000, 2,000 probes. And attaching BPF programs to about 2,000 probes can be a very time-consuming business to get done. And we brought it up with the BPF maintainers. And one of them, his suggestion was, well, if you just do one big program that can serve all those probes, you can load it once, attach it to all different probes, and that will work, which is very ugly. It's not really a good solution because you're just going to have one big program with a very large conditional that says, okay, if it's probe A, then do this, probe B, then do this, probe C, do this. So we're really hoping to have a more sound solution to that, where we don't basically have to load a program to every single probe, of which maybe only 10% of the program will be used. Another problem with BPF is it has a small stack. It's 512 bytes. Yeah, which we can work around because the way, fortunately, the code can be compiled, and the fact that it was originally designed to compile on an action basis helps us, because it means that basically you don't really have that much stack need. The problem comes in when you have pre-compiled code. We have this library of functions that implement things that are not available in the kernel for BPF. Things like, for instance, taking a substring or converting a string into an integer, things like that. They're compiled with GCC, which assumes you have a reasonable stack. So if you have a couple of these functions that are being called, especially in nested levels, you very easily blow through those 512 bytes. So we had to be very creative and conservative in how we write our code, which has also resulted in the decompiler to be a little bit more ugly than I would have liked. And so, in summary, it always comes down to the BPF verifiers. If that was not happy, your program's not going to load. So that is kind of the measure we always have to work against. And so we sometimes will go for larger programs with less complexity in order to make sure that we can do that. For more information, so the source code is available on GitHub. It should compile on pretty much any Linux system with a recent kernel. It does depend on the BPF cross compilers with GCC and binutils. And, it works. I mean, we use it in production. We use it to develop dtrace. Yes. One of the coolest things I found is that you actually can trace dtrace with dtrace. Nice. How it works. So yeah, it's been a joy. So thank you.
That's great. Thank you, Kris.
Yeah,
Thank you very much.
So, I've got a bunch of questions.
Okay.
Brian, why don't you come on the camera?
Sure.
Hi,
camera. I've got a bunch of questions.
Mhm.
One, So because we've been using BPF trace to help debug some, to get a guest's perspective. So we're running hardware virtualization.
Yeah.
And obviously we've got dtrace, the hypervisor, but we don't have it. So I'm very interested to be able to use actually dtrace on BPF in these guests. One of the frustrations has been with dropped data from eBPF.
Okay.
Because in dtrace, we try to be very careful that if we drop data, we indicate that we've dropped data.
Yeah.
And I'm still not convinced that I wasn't, I think I may have been holding it wrong, but I was getting silent. It's very hard to know if you're getting silent drops. I mean, so yeah, is that something that so obviously it's on BPF to get the UBF to get that right.
Yeah. We haven't had, I mean, we've seen drop data, like we've seen it in general with dtracing before. I think in almost all cases that I can think of, it is being reported. And that is something that we actually spent quite some time in, is to make sure that the drop counters reports is there. Because that was something we were missing in pretty much any other tool.
Right.
Because the advantage is that actually the biggest drops that occur is basically if it cannot be written to the perf event buffers. And that we have notification for. We actually can provide information.
And so you wire yourself up to that notification.
Yeah.
Okay.
So that is not a problem. So those
Yeah.
we've had, what we have run into is that the perf subsystem in some cases, for lack of better terminology, is refusing to fire a probe. And there's not much we can do. Timer probes on some architectures are an issue with that, depending on the kernel configuration. And so, yeah, tick probes, for instance, and profile probes have been inconsistent. And we have been trying to work with kernel developers to find out why. Because it's actually not even anything on the BPF support side. It's actually really in the perf subsystem that it seems that either they're throttling it for some reason. I know one of our developers thought he had a solution for that, but then it still starts happening. So it feels like a situation, and we've encountered in a couple of other cases where the system is somewhat working against us.
Yeah.
But it's the tracing world. We're trying to convince the kernel developers who are so performance driven, which is very important, that, well, if you can't guarantee that the tracing infrastructure is going to be accurate, then they might as well not have it. 90% working even 99% of the time working is not good enough, because the 1% is where we're going to fall down. So that's still a work in progress, but I think it's a bigger problem within the kernel where the data is essentially not being generated.
Yeah, because the frustration that I'd had in particular was trying to pair up events, like an IO starting and an IO completing, and you want to know how long these things take. So it's actually important that you get both of these events.
Yeah.
And if you get drops, you just want to know, like, okay, I've dropped this, so I've lost coherence.
Yeah. And one of the problems with that as well is, and that is where Linux is more of a challenge, and that's why we put a lot of work into the different STT providers that these provide that are documented, because then you have a better notion. Like the IO start and stops. I think at this point we have pretty much figured out that we can support them where they're correct.
Oh, wow.
But that took some time because not all execution paths run the same way.
Right.
And so the IO start usually is very easy to find.
Yep.
The IO done may come from 5 different places. So that's where under the covers, we are actually tapping into those different trace points. And some of them are NPT probes that we place. Some of them are trace points the kernel has. And we synthesize them into one.
So that alone is actually hugely helpful, because I'm not convinced that I wasn't missing one of those paths. I mean, because you're looking at the source code, just like, I hope I've got all of these.
Yes. Had similar problems. I think early days of dtrace STT, like it would be when you are placing probes by hand, it's possible to forget, actually there might be some completion over here or whatever.
Yeah.
So the fact that you're adding those things so that every consumer of that conceptual event doesn't need to do that exercise seems hugely valuable.
It is, but that's the power that dtrace has, that it has those documented SDT providers for IO, for SCAD, for proc, and they can hide what is really going on in the operating system. This also makes it possible. I know for some of them, we actually are attaching to different probes depending on different kernel versions.
Right. And you're abstracting that.
But
which
yeah,
is-
we're abstracting, and we synthesize it into the providers that dtrace.
and then
device.
and when you and then this works on different distros that have, as long as they've got eBPF.
Yeah.
So I can run it on Ubuntu.
Yeah.
That's
Should work.
That's great. We're going to use it. So thank you.
Yeah.
No, I mean, this is going to be super helpful. So thank you very much. This is really great. And what has been the uptake? I mean, obviously you are using it. Have folks started to use it?
We've gotten more. We've had some, I know Gen 2 has added it to its distribution very recently.
That's great.
So it is becoming, I think people are starting to pay attention more again. I think what fell by the wayside as even, I don't think this break for the fact that I think it's persistently still existing.
Yes.
moving forward.
All credit to you. Like,
So I
that,
think
that is still existing. That's great. Well, thank you. Thank you very much. I think this is going to be, this is great because I think by implementing it this way, you just get, you are now going to be present in a lot more distros, which is
Yeah, and hopefully that will also encourage people to help to contribute.
Yep.
And move things forward, since we want to keep going forward.
Yep. Awesome. Kris, thank you so much. And thank you so
Okay.
much for being here.
Yeah.
Really appreciate it.